in the NAMD simulation. So let's go to the TCL file, which I named as, let's see, okay. So in this line, if we remember correctly, then we give a different selection here, which was chain B and helix, but somehow it didn't recognize that command and flag our beta column with 1. So I changed it. If you remember, then let me quit this file first. So if you remember, then we create a text file which contain the residue IDs in the helix of our chain B protein. So let me find that protein and find that file. Okay, I think it was const.txt. Yeah. So these are the list of the residue IDs on which we are going to apply the constant. So applying the constant means we will increase the strength of the spring, which we assume that the bonds or the two atoms are connected with these springs. So bonds are approximate to the springs to do the calculations. So by applying constant, we'll increase the value of the spring constant, so that the atoms which are connected to the bonds will have a very local kind of vibration or motion. And by fix, we'll literally fix the atoms in the space. So these are the list of the residues. We'll use these residues to prepare to flag our beta column. So let's go back to the TCL file here. So these are the residues in chain B on which we'll apply the constant. So now let's run this file in VMD. Remember the name of the output file we will write is constant.pdb, and we can name it as we wish. We can give any name for the output. Okay, so we can open up the VMD and source this TCL file from the TK console interface, or simply we can do VMD and input our script file, this file. So in this way, the VMD will take in the commands from TCL file and execute it, and it will give us the output if everything is okay. So we will run this. Yeah. It will run it and quit by itself. So let's look at the output file if it is generated. Oh, sorry. Yeah, this was our output generated. Let's double check before we proceed, because there can be some mistakes that we have committed during the process. So it's always a good idea to double check everything before jumping into the next step. So let's double check. Okay, so this is a standard PDB file. So as we discussed earlier, that these two columns are the occupancy and the beta column. So we are going to manipulate this beta column for the purpose of constraint. So here 0 flags are the no constant, or the constant is off. So they have a freedom to move according to the force field. But if they are 1, so they will be constrained in the space. So let's check if we have Okay, first let's display the list of the residues for which we expect the beta column to be 1. So I will simply cat this file. So these are the list. Let's check a couple of residues if they are correctly flagged to be 1. Okay, so let's check 603 for this instant. So this command will search for 603. Okay, but this is a atom entry, uh, atom serial number. So this is not what we're looking for. We're looking at the residue ID, which is this column. So if we type N, then it will take to the next search, next appearance of our search string. So this is chain B and 6. So if you look at this, from here our constant has started now. The flag is 1 now. So again, check if 64 is to be flagged 1 or not. So let's check this file. Here is 64. Oh, sorry, 604, 605, da da da, da till 684. Yeah. So 4 is also flagged correctly. Let's go to the 684. Six 84. Okay. Yeah, 684 is also correctly flagged. Then afterwards there is 0 flag. That means they will be free. Seems like we have made this file, generate this file correctly this time. So this time we use the beta column to manipulate it to flag 0 and 1. We can also use occupancy column. So if you want to do that, then we can simply change the TCL file in place of in place of beta, we can simply change it to the occupancy. So if we change to the in place of occupancy beta, we can change to occupancy, or if I remember correctly, then this is the keyword for that column. Okay, you can give a quick search if you are curious. Then for now, let's keep it as beta. But the point I'm trying to make it is that we can also manipulate occupancy column to manipulate it to flag 1 and 0. But we also need to specify it in the NAMD configuration file. So after we have successfully generated this file, which is the manipulated file, and we flag the beta column to be 1 and 0. So we'll use this file in the configuration, named configuration file. So let's go to the, before this, let me copy this PDB file. I think I will be needing this file in there. Okay, these are, okay, I think I will make a copy of this. I don't want to miss this file. Okay, I will copy to, let's say, constraint.config. Conf. Okay. Then, okay. So everything will remain the same, but we need to change the block of this constant. We already have the commands, but they are silent now. So we can we can make them active by removing this pound signs. Yeah. So this command says the constant is on. This is the cons exp. This is the constant of the spring that we need. I think. Sorry, it is the value of the spring constant. So we can also increase this file, but let's keep it. I think. Oh, sorry. Actually, I don't remember this one. I think the constant is scaling. This is the spring constant, I guess, but I'm not sure. We can double check it, but I will not do it. If you are curious, then you can do it. I think the constant should be this one. I think this has to do with some integration, numeric integration there. Okay, this is the reference file which we keep. So generally, the atom entries for this cons.pdf, which are flagged, will be same as this file, pro.pdb file. The only difference is the flag in the beta column. Okay. This is the reference file. Then actually this should be the pro.pdb file from where we take the reference, and this is our constant file in which we flag the beta column. And here is a bit const column is B means beta. And similarly, if we want to do the const column to be occupational column, then we can change it here. I don't remember the keyword for occupancy. It should be O. That's my guessing, but we can double check that. Yeah. So that's all. So we just make them these commented commands to be active, and basically all the other things will remain the same. So we only just need to make use of these extra commands to apply the constant. Okay, so that's all for the configuration file. So let's write and quit. And okay, let's also change the name of the output. Oops. Because it will overwrite everything, overwrite the files that we generated in our previous simulation. So we don't want that. So let's direct our output into different folder, and we'll create that folder in our working directory. Let's make it cons. Okay, override and quit. Let's make this folder here. Okay. So now we're ready to hit the simulation. Command to run the simulation is NAMD2. Name of the configuration file. Then we will redirect the outputs from NAMD simulation to out const file with also CV. Okay, something like that. Let's hit the button. Yeah, the simulation is running, but let's output the. Let's see the output on this console. terminal, I mean. Yeah, so it's running. Let me cancel this and again redirect the output to our txt file. So we're not seeing the outputs here because the file is, these informations are being written on this file. So we won't see the output in the terminal anymore. So yeah, this is how we run the constant simulation. Again, if you have to restart the simulation, the procedure is the same. So you just mute the temperature commands and mute the minimization part and assign the initial step from where you want your restart, then everything is same. So this is for constant. In case of fix, it's almost the same. You just unmute the, okay, let's copy for zv fix dot conf. Okay. Oops, sorry. Copy. Okay. Let's vi this file. Okay. So for the fix, you can change it to fix. We'll make a different folder for the outputs from fix simulation. So everything remains the same beside this block. So in previous step, we make use of constant block. Now we will use this block to fix the atoms in the chain B and in the helix. Yeah, it's simply run this command. It will turn on the fix command. Then this is again the PDB file, atom file, which is the flagged file, which is this constant.pdb, this file. Okay. Oops. I think, yeah. Okay. Yeah. And again, we are using beta column here for the reference column. Okay, that's it. So, and other process is the same. We'll write and quit and make out fix. What was the, okay. It was out underscore fix. Okay. Yeah. So you can again run NAMD, then the configuration file. Let's see the, oh, there is something wrong. Cannot open this PDF file. Okay, I think that's a, we are missing S. I think we named the file as, oops, const, yeah, we are missing this character. Okay, let's fix it. Then, okay, yeah. Let me cancel this. Similarly, you can redirect it to the out, fix, then fix.txt, something like this. Yeah, it's now the output is being written here. Okay, so we need to wait for the simulation to see the difference. So you guys can run this simulation for a certain time and visualize the trajectories. What are the difference in free simulation, in constant simulation, and in fixed simulation? So we already finish our simulation with the free simulation, where every atoms are free to move. So we will visualize that simulation now. But for this fix and cons, we need to wait a little bit. We need to wait for some time to finish the simulation and load them and visualize them to observe the difference. Okay, I'll open our new terminal. Then let's visualize the trajectories from our previous simulation, which was free. So let me open up BMD, then file, new molecule, browse. Then let's first load the protein structure file. On top of this, we will load our DCD files. So our initial DCD is here. So the simulation was stopped at some point, and we restarted the simulation. Okay, you can wait till this simulation to fully load, or we can simply load our another trajectory. So this is the folder for which where the outputs of my restarted simulation are. So this is the another trajectory. Oh, first let's load let's load all of them first. Okay, so we have 62 frames, so it's not completed. So we can now load this and see how far it goes. Yeah, we have altogether 8 frames for 1 nanosecond simulation. You can control the number of frames by controlling the saving the DCD frequency time period. In that way, you can control. For current setup, we have obtained 800 frames. So we can do a little math for that, how we get this. I remember we had a 2 million total steps, and I think we saved it in every 2500 steps, if I remember correctly. So we can double check. Let's see. Let's see one of the configuration file. Oh yeah, we have 2 million, and we saved our TCD frequency in every 2500 steps. So if we divide this number with this, I think we'll get those number of frames which are loaded here. Okay. Yeah, this is how we can load our trajectories. Even we can have like multiple of restarts, and you can simply keep on loading the other DCDs you have, and it will like append the DCDs file which you loaded later. So you don't want to do this in every time when you open up the VMD and try to visualize your simulation. For this, either you can save the current session by saving the visualization state. By doing so, we can I think it's worth to give it an example here. So for now, I will save the visualization state here. So I'll save it in somewhere here inside the NAMD simulation folder, and I'll name it as total trajectory .vmd, something like this. So okay, so it will save it. So let's delete this current loading and load the saved visualization state if it was written successfully. So if you go to the load visualization state button, then oops, let's see. It's inside this folder. I don't think we write it correctly. Let's see. Files. Okay, just a moment. Let's check our couldn't open error opening file. Oh, I think it didn't write it correctly. There are some errors here. Oh, instead of saving, I think I clicked the wrong button there. So we can do it one more time. Let's try one more time. So there are certain warnings. We can get this on the interactive terminal of the VND, so we can get the idea what's the error. Generally it shows the process, what's going on. Every time you make the selection or do whatever, they will give you the status here. So this will help us to know our mistake. Okay, let's try to do it one more time. Browse, then PSF, load, then browse. Oops. Okay. Load, browse, load. Okay. Okay, it's fully loaded, and file, save visualization state. Okay, this time I'll double check if it is written correctly or not before I close the loaded VCD. Okay, it's in there. Check this. Okay. Let me open the new VMD. Then load visualization state. Yeah, now it's here. Then okay, takes some time to load the, yeah, if you see here, this is our new VMD window. These are old one, older VMD. So let's play it. Oh, we didn't see anything weird. Oh, this button is off. Yeah, because when this happened because while I was saving, I hide the display here. So it write exactly the copy of that state in the new VM new state. Sorry, when I open the saved state, it will exactly open me at the point where my saved point was. So it also gave me without the display here. So I need to open up this display button to see my system here. Okay. Yeah, this was the original. This is the VMD for our loaded visualization state. Yeah, which we saved from this work. Okay, let me close this one. So this was how to save the visualization state, but this is also not quite efficient for the purpose of all the different analysis. We need a one solid concatenated DCD file. So after loading all the DCD file you have, you can write your DCD file. You can select this file, highlight this PSF file. You may also have like multiple of loaded DCDs at the same time, and select the desired simulation you want to concatenate together. Highlight that and go to save coordinates. Then go to, they also have a box for the selection. So for here we will save all the items. You can give the desired if you only want to have the DCD file for a certain portion of your system, then you can give it a selection. For example, if there are many other components and if you only want to save the protein, then you can save the protein like this. Or if you want to have the trajectory for water only, you can save it as water or ions or any other ligands that you have in your system. So for now, I'll save it all, and you can change the file type to be DCD. Yeah, we can. We also have a flexibility. There are also choice for the range of the frames. So this is the first step, last, and this is the step size. We can also save it from somewhere 500 to 800 or as per we like. And we can also choose the step size. So let's save the total trajectory. Let's save it in the same folder as total dot tcd. Okay, so let's double check if the file is written correctly. Whether you can check the interactive the status in the VMD terminal. It says with coordinate file, this and that. Yeah. So let's also double check in our current location. What was the name of the file again? Oops. Okay, total trajectory. Yeah, it's there. So let's again load this trajectory if we get the 800 frames or not. So I'll open up new VMD, then new browse loaded PSF. This is the drill to open the DCD file. Either you can also load the DCD file first and load the PSF file later, or the vice versa. Both will work. Then total DCD. What is it? Yeah, load it. Let's see. Let me hide it to help to load the frames faster. Yeah. So these were the total number of frames as in the initial frame. So we can make use of that frame either to load, visualize our trajectory, or do other post analysis. Let me close this. Yeah, that's all about how to load the trajectories and play with the trajectories and do certain manipulations. So now, this is all about the uh, implicit water model, where we didn't use the real water molecules. We only give their parameters in the program so that they will assume that as the implicit water and implicit ions. There is another technique in which the simulation make use of real atoms for water and the ions. So that is called the explicit water model. So today we're not going to talk about that, but we can talk it in future if you guys are interested, and we can talk about that too. But for now, I will show you guys how to do the similar things in supercomputer. Basically, how to transfer our files from local to the supercomputer and run the simulations there. So by doing so, we can make use of the huge resources available in the supercomputer. In that way, we make our work faster, and also we can run the simulation for a longer scale of time. Okay, let's do this. Do that. So for that, we need to have a account in the supercomputer for our current works. We are using supercomputer, which is at University of Texas at Austin, I guess. So they have a huge supercomputing center. I think it's one of the top 4 or 5 biggest super or powerful computing center. Okay, so for that you need to have a account. I already have one, so let me first log in to my account and find my working space there. So to do so, we will make use of the secure shell command to connect our local computer to the supercomputer, which is SSH. This is a secure shell. So I'll also provide a flag like this. This is an X window, which helps to visualize our programs in supercomputer, linking with the help of our local computer. Generally, the supercomputer they have the Linux environment and they don't have GUI option there. So we can supply this command to run certain GUI versions of certain programs to visualize our system or proteins. So the -X is for the X window, for the to see the visualization in our supercomputer. So then the username. This is my username at the rate. This is the supercomputing cluster name, then video. Oh, I think I mistyped somewhere. Stamp to dot video. Mm. Again, there is a typo here. Oops. Stampede. Oh, I missed the TSSE. Yeah, I missed the TSSE here. So this is the so they will ask for your password. I think I mistyped my password. Sorry. Yeah, they have a double layer of security. They ask for the password and some token number. So you can get the token number. You can set up your account to get the token number via SMS, or you can make use of application to generate the token, which is synced to their computing center, and they keep on generating the token code for you. Let me find my code. It's right here. 26. No, I think there's a time limit there. So let's do it one more time. Four, 9, 6, 2, 3, 9. Okay. Yeah, this time they let us in because I typed in everything correct. Okay, this is there are certain informations we get at the beginning of our login. While we log in, they will give us certain information at the initial point. So, yeah, this is our project name. This is our available SU units. So these are the units we can make use to have the computation there. So generally we can apply like how much SU units we require for our projects. So this is the expiry name. Oh, we have two projects. Oh, cool. I didn't notice. Yeah, we have this project, and we have two projects there with 5,000 units and 17,000 now. Okay, these are the expiry dates. Okay. So these are the different folders that I have in my supercomputer. They have assigned us three different working spaces or directories. This is home, work, and scratch. By default, they will take us to the home folder. So if you print the working directory, so yeah, we are inside home. By default, we'll inside home once we log in. So if you wanna go to, basically the space for this is limited. So it's around 10 gigs, I guess. Yeah. This is in gigabyte units. It has a limit of 10 gigs, and I have already used 6.8 gigs. This is not enough for a very large scale of work that we usually do in our lab. So it's a good idea to make your working directory at work folder. So it has a big space, which is 1 terabytes almost. Yeah, it's 1 terabyte. I already use up half of it almost. Okay, let me. And this home folder is suitable for storing your softwares or your two different tools. And by doing so, we can easily have access on this folder. Yeah, by simply giving the command like this. So it will take us to the home folder. So let's see what's inside my home. Yeah, these are the different. Okay. First, let me change this directory. Also, what do I mean by this? So if I wanna go to the work directory, I can simply type work w. This is the shortcut. Okay, this is the shortcut, or you can also type cd dollar work, something like this, to go to the work directory. Okay, so from the work directory, if you let's say list your home directory, then it will give the folders and files in my home directory, so it is easily accessible. So if you want to locate uh, your working directory, then sometimes it's a quite lengthy path you have to type in, you have to get. So it will be easy if we have if our programs in home directory, so that we have easy access with only this command, with this kind of mm, tilde sign and the backslash. Okay, now I'm in the working directory. I have a couple of folders already there, so I'll make one more folder. I'll say NAMD same class. So I'll copy all of my files from my local computer to this folder in supercomputer. First, I'll make the directory. I'll go inside that directory, print working directory. We'll be needing this directory while we copy our files from local computer to the supercomputer. Okay. Again. I'll open up a new terminal here. Okay. So these are the files that I want to copy. So either I can copy all of the files or I can copy the folder. So I will copy the folder for now. So I'll go one step back and, oh, sorry. Yeah. So to copy this, here is our folder in which we have all the files required that we worked on. So I mean, that's in desktop location. Yeah, it's in desktop. So to copy, we need a command which is super copy. So if you want to copy the folder, then we'll use flag -r. This means recursive. So it will copy all the files inside our folder. So if you want to make the copy of only the files inside the that folder, you can do copy NAMD simulation, then asterisk. This means all the file inside that directory. You can we can do either of the way. Okay, for now let me copy all of, all of the files. But if you want to copy the whole folder, then you can make use of the flag dash R, then the name of the folder. This is our location of our folder in local computer. This is our source. From here we want to copy our contents to certain destination. So we need to provide the path for the destination. So which will be edu, then colon, then path in the, okay. So this was our path. Let's copy this path. This is the working directory in our supercomputer. So this is our supercomputer. Then this is the location inside the computer where we want to copy out all the files. Let me double check if everything is okay. So this is super copy. These are location of our file and the files. Then I think there we also have folders inside our named NAMD simulation directory. So I'll make use of this R. It will help to copy me files and folders at the same time. Okay, then my username, then working directory. Okay, let's give it a try. Okay, again it's asking me my password. Oops, I keep on typing my password wrong, I don't know. Okay. Then the token, it's 65702. It will give the status, so it will take some time. So if you have if you have files in a big number, then it's a good idea to compress our whole folder and transfer it. In that way, it is much easier. You see, if you have a big file, then it takes time. So if you have a compressed version of our folder, then it will save us time. Yeah. Every folders are copying. Let's see if we are getting these folders in our destination folder or not. Yeah, we are getting. Yeah, this was the folder that we recently created, and it was empty. We didn't have any content inside this folder. But for now, if we list inside this folder, then we have contents now. Yeah, we already finished it. Again, list this. Okay, let's go to our folder. Oops. Okay, so in the supercomputer, there are like thousands of nodes they have, and inside a single node, they again have, if I remember correctly, then it is 68 threads in them. So node is like a single computer. Yeah, so we'll make use of multiple of nodes and threads to run NAMD simulation in a parallel fashion. In that way, we run the simulation, we get our simulation results faster. Okay, for this we need to submit our job in the supercomputer with some commands. There are certain file systems, certain parameters designed way to submit our jobs. So for NAMD, we have this file here. Okay, in this file, we need to assign certain things to submit our job. So these are the sbatch commands. So this first line is the name of our job. So we can give a unique name for our job. We will say NAMD class or something like this. So this is the output for the error files. Yeah, this is the name of the queue in their system. So we'll have different types of queues here. So this is the normal queue. So if you want to look, if you want to know like what are the different types of queue we have, then you can give it a, can look this information in the Stampede user guide. Oops. Okay, here. So they have a different, like you can get all the needed informations here. Like you can get all the needed information about the supercomputing center here, about their architecture, about the different modules they have, and different file allocation systems, about the projects, how to connect to them, you know, how to use them, or how to get the environment for different programs they have installed in them, and many more things. Yeah, and how to submit the jobs, how to get the interactive nodes, something like this. So you can take a look at this user guide, yeah, about the folder system they have. Yeah, many more things. Oh, let's search the queue. Did I type it correctly? I don't know. Let's see. Yeah, these are the different queues they have, and depending upon the name of the queue, they have a different time allocations for them. I mean, the limit of the time, the cost of the SU units, something like that. So we are using normal, and in normal they have 256 nodes and this much of cores. We can make use of this number of nodes and cores in maximum. So this is the time limit. So we can only have facility of 48 hours for our job. So 120 is the longest, which is the name of under the name of the queue long. Yeah, but the limitation of the job is only 2. If you see the limitation, max job in queue, so we can only submit 2 jobs if we use long queue name. So in normal, we can have up to 50 jobs together. Okay. Let's go back to this window. So that was the name of the queue. This N, capital N, is the number of nodes that we are using, and these are the number of threads that we're using. So in total, we'll be using 4 times 52 cores, threads. Mhm. So this is a comment. So if with the SBATS, if you have a single pound sign, this is not a comment in here. This is the command. But if you have a if you want to make a comment, then you can add other pound signs to make it a comment. So this line is not working in here. This is a comment line. Mm. Yeah, because we already defined the normal. We are not using development. You can delete it or leave it like that. So this is the time, how long we wanna make it run. So we make it 48 hours. This is the maximum limit. So on the basis of the time you want to take the resources, they will have different levels of priority. So if you ask for a less number of hours, then they will give you top priority. So if you have a longer period, then the priority is less. So to give it a trial, I will just ask for, let's say, 1 hour, but I'm not sure 1 hour is enough for our job. This is just for example. So yeah, we need to assign the name of the allocation or the name of the project that we have. Here is a SAT6, and we don't have this project existing. It already expired, so I need to change it here. So let me double check the name of the project, which were here. So I'll make use of this project. I'll copy this and I'll paste it here. Okay. So the good thing about submitting jobs is also we can give our email address so that we get the email once our job is started and once the job is finished. So we have email address of Dr. Lee in here, so you don't want to do that. You can change it to your own email address. I'll change it to be mine. And the rate minus U tab uncomment this lines. Yeah. So this is, they will email us once the job is began, and they'll also again send us email when the job is ended. Okay. So this command will help to load the programs. So they have a huge list of huge programs there, but they are not loaded once you get log into their system. To have the access to those programs, we need to load those programs, or we need to call those programs. So to call the NAMD program, we make use of these commands. Module pers, it is needed to load the modules. So this command is needed to make use the parallel version of NAMD program NAMD. So these are for loading the NAMD, and this is the command to run the NAMD. So these are some fancy looking some commands here. These are for these are the commands to run the NAMD in a parallel version. Actually, I don't know the real meaning of this, but I take this example from their help page. Okay, basically when we run the NAMD simulation in local computer, we only used NAMD, then the configuration file, then the output. In here we have some extra commands. These are for parallelization part. Okay, so I don't have that much idea on these commands. Okay, so I want to skip this part for now. So we need to supply the correct configuration name of the configuration file here. Okay, I think this is our initial configuration file. Then we will make a new directory in the supercomputer as well. So I will make it out supercomputer, let's say. Then we'll write and quit. Okay. So to look at the different modules or different programs in the NAMD, I think we can look at the if you try module spider, let's see, they will give us all the list of the programs they have. So if you see, they have our studio something. These are the different programs they have. They have it in there. So if you already know which program to use, then oops, how do I quit this? Quit. Okay. If you already know the program name, let's say for NAMD, then we were using 2.0, have different version of NAMD installed there. Yeah, something like this. Then it will take you to the help page for that. These are the different help pages, how to run the NAMD in TSCC. They also have some examples here. They give example for different combination of nodes and the threads. I make use of this example. I make use of 4 nodes and 52 threads, and use this command here. This one. We can also get those kind of help information for other programs that you want to use in the TSCC as well. Okay, let me quit this one. So we do some changes in our job file. Then now it's time to submit the job. So let's double check. In the job file, we said we will output our outputs files from NAMD in this folder, but we don't have it. So we need to make it here. Let's make the directory here. Okay. So again, in the configuration file, we don't have this folder here. So if you look at this configuration file, we have out. We will save our outputs in this folder. So this folder doesn't exist, but we agree to have this output folder as this one. Okay, so we are all set to go now. So to submit the job, we need to make use of this command as batch, then the name of the job. So here it. So they will request, we are requesting the job in their system. So based on the priority, they will assign the number of nodes and subnodes, and they will run our job for the time that we have requested there. So let's to look at the status of our job, we can see the status of our job. So we can make use of command mm, okay, just wait. I create some allies, but yeah, yeah. Don't be confused with this command. I make allies, but I've forgot the full command for this. Let me quickly look at this. Yeah, SQ. Yeah, this is the full command. Yeah, this is the SQ, which is the super queue. Then dash U is the name of the username. So they will give me the status of my submitted job under my username. Yeah, so this is pending. So once they take in our job and it starts to run, we will see the time here, and and it will generate the files inside this file. Yeah. Oh, yeah. This doesn't make any sense. So once it starts to uh, run, then it will give us output something like these. Okay. Yeah. Yeah. This is how we. Oh, it's already started running. So the status is here. So this is our job ID. This is the name of the partition that we used. This is the name of our job. This is my username. This is the status. R means running. So it already ran for 104. I think they take our job in high priority because we only asked for 1 hours. So yeah. So these are the 4 nodes. This is the one node. Then these are the 2 nodes, 402, 401, then 402, 072. Then this is the 4th node that they assigned for us. Yeah, that's why we are saying the outputs in out. So let's tell the, yeah, it's running. See, yeah, they are very fast. In yeah, they already finished the minimization part, and yeah, in like 1 or 2 seconds, they already calculated the 1,000 steps. Here was 23,000, and here's 24,000. Let's do one more time. Yeah. Yeah, now they have 27. See, in like 2 or 3 seconds, they run a huge number of steps. So this is faster. So in this way, we can run the simulation in supercomputer. So we can wait till the simulation finish, and everything, loading everything is the, so after all of them, all the simulation is done, then we can again download, we can copy those outputs to our local computer and do our analysis, or we can also use VMD in supercomputer to do our analysis. We can use VMD or Chimera or other different tools that are available in supercomputer to do our analysis. So it's up to us. So I think I would like to stop here for today. So maybe in maybe I want to take one more lecture to show some other advanced things, how to use VMD or something in supercomputer in some other time if you guys are interested. Also, you guys can ask me anytime if you have some confusion or if you want to know more about these things or where to look at. So I'm always happy to look at this. So that's all for today. Thank you, everyone.
Thank you.
Yeah, thank you.
Thank you so much.